Welcome learners. Today's topic of discussion is Sturm Theory. Sturm Theory is a part of our course Differential Equation and Numerical Analysis. This is a course of our MSc program, MSCMACS. This is the topic which is very important because this topic is part of our course, but it also important for various competitive exams like national eligibility test, state eligibility test, or for interview purposes for different exams, especially for the students who are going to continue as research in the area of differential equations. Now let's see what we have. So before starting this theory, let's start the importance of this theory. This theory is very much important because of we know some important polynomials like Chebyshev's, Lagrangian. These polynomials are important, but we want to categorize that how we can generate this type of several polynomials and what type of equations which generate this type of solutions. Okay, so let's start. So before going to this theory of Sturm theory, we need some preliminary notions. So we are going to learn some preliminary theories like self-adjoint and adjoint equations and how we can solve it, and what are the benefits of identifying adjoint equations and self-adjoint equations. So let's begin with self-adjoint equation of second order. So suppose we have a second order linear differential equation with coefficients a0, a1 and a2, where a0 is not equal to 0 and continuous and first order derivative. So we'll see why we require these properties of these coefficients. When we see what is the definition of self-adjoint equation, we'll understand why we need this type of properties of these coefficients. Let's go to next slide. The adjoint equation. So this equation is the adjoint equation, where you can see that a0 we need second order derivative of the coefficient a0 to be well defined, and we need first order derivative of the coefficient a1 so that it become well defined. So that's why you will see that we have assumed those conditions over those coefficients, so that a0 should be second order derivative continuous, a1 should be first order derivative continuous, and a2 should be continuous. If you just simply differentiate and expand it, you will get this second form. Let's go to the next slide. Example. Let's see an example where the equation is given and we are find out the adjoint equation of the given equation. So you just see the definition, we have applied it, and we are expanded the given equation in the form of its adjoint equation. So the first equation is the given equation and next is the adjoint equation, and if you simplify it, you will get the third equation. Next, go to the next slide. Self-adjoint. What is self-adjoint? So if a equation and its adjoint equation are identical, then we say that they are self-adjoint equation. We'll see very shortly what is the benefits of identifying self-adjoint equations and several theory related to it. Now let's move to our next theorem. So necessary. So how we can identify self-adjoint equations? So this is a necessary and sufficient condition for self-adjoint equations, where if the derivative of a0 becomes a1, so the original equation and its adjoint equation become identical. So this is very simple proof. You just put a0 dash in place of a1. So if you see the definition of adjoint equation in the expand form, now put there a0 dash equal to a1, you will get this. And now if you just simplify it, in the next slide you will see this, where the self-adjoint equation becomes this. So if the second order homogeneous differential equation is called self-adjoint equation if the given equation and the original equation are same. Next, see an example. This is a Legendre equation given, and the next slide you will see its self-adjoint equation. Now let's see a theorem related to this. Any second order homogeneous differential equation where these coefficients satisfy these conditions, we can write the given equation in the form of its self-adjoint equation. So basically this theorem state that any given second order linear homogeneous differential equation can be transformed into a self-adjoint equation if we apply proper transformations. So you can see if we just multiply both sides with 1 by a0 exponential to the power a1 by a0 dt, you will get we can transfer the original equation in the form of self-adjoint equation. So let's see the proof in the next slide. So you can see just multiplying by a factor this 1 by a0 exponential to the power this, the original equations. If we just multiply this with both sides of the original equation become the second equations, and then after simplifying you will get the third equation. So basically this proof is not much difficult. You are just multiplying by an factor to convert a given equation into a self-adjoint equation, and the new equation becomes self-adjoint equations. Next, see an example. Here this is a given equation, second order ordinary differential equations, and now we are multiplying as per our theorem. We are multiplying by this factor which is equal to 1 by t to the 4. So the given equations become this, and then we can write it in the form of a self-adjoint equation. Next, self-adjoint equation of second order. So basically in other words we can say any self-adjoint equation can be written in this form. So whenever we are talking about self-adjoint equation, we'll only consider equation of this form. Next, theorem. Let f be a solution of this equation where f has first order derivative on this interval and f has infinitely many number of zeros on this interval, then f is identically 0. So this is an important theorem. Here we can see the benefits of self-adjoint equations. So if you have a self-adjoint equation, we can identify some properties of the solution, then we can identify the complete solution. And here, if this property satisfy, the solution becomes identically 0. Let's see the proof in the next slide. So since the solution has infinite number of zeros, so there is a sequence of zeros, and as per Bolzano-Weierstrass theorem, any infinite set has a limit point. Infinite bounded set has a limit point, and the domain of definition here is a comma b, so it's a closed bound set, and here you have infinite number of zeros, so it should have a limit point. So the sequence of zeros should converge to a point which is t0 by Bolzano-Weierstrass theorem. So, and again f is continuous, so therefore the limit t tends to t0, f of t equal to 0, actually f of t0. Now we have also assumed that the derivative exists. So what is f dash t0? This is f dash t0. Okay, so since this point, now this f dash t0, if we look at this definition of the derivative, we see at t tends to 0, this limit should exist. So we can approach t0 as per our choice of points. So if we choose the points such that all the points are actually the points of the sequence which are converging to t0, so if we choose these points for this limit, then the ratio of this limit becomes 0. So therefore the derivatives at t0 also becomes the 0. So now we have a situation where f is a solution such that f is 0 at t0 and the derivative of f is also 0 at t0. Hence f is identically 0, because see, this is an second order differential equation. So at most it have two linearly independent solution. So f must have the linear combination of these two solutions, and if you apply this initial condition, both the coefficients and linear combinations coefficients of the linear combinations will become 0. So hence the solution becomes identically 0. Next, in the next slide, we see another important theorem. Let f and g be two solution of this self-adjoint equation, and then we show that this term is a constant. Now, why we are interested to this theorem? This theorem is important to prove the next theorem, which is important. But this is just a mediator steps which we need to prove a bigger theorem. So that's why we are also proving this mediator steps as a theorem. So what this theorem basically states, if you have two solutions, this terms it becomes constant. In the next slide, we see the proof of this theorem. So since f and g both are solutions of the given equation, so they must satisfy the original equations. So if we multiply the first equation by minus g t, so the first equation comes from as f is a solution, and the second equation comes from as g is a solution of the given equations. Now if we multiply by minus g of the first equation and f by the second equation, so and add them and integrate them, you will get the original result. Now how we are finding that by what we should multiply this equation? If you carefully observe this term, that f of t into z dash t, that we are going to prove that this term is equal to constant. So if you carefully observe, what we actually need to find, f of t into z dash t equal to f dash t minus f dash t into z dash t. So we have, where we have f dash derivative of f, there we need to multiply by z, and where we have f we need to multiply by z dash. So in the first equation we have f dash, therefore we are multiplying by minus g. In the second equation we have z dash, so therefore we are multiplying by f, and then adding them and integrating them results the required solution results. In the next theorem we are proving another important results, where let f and g be two solutions of these equations, self-adjoint equation, then and if they have a common 0, then f and g becomes linearly dependent. So this is another way to finding out that these two solutions are linearly dependent or not. And all these important results, good results, are only true because of these self-adjoint equations. So these are importance of self-adjoint equations. So first we are trying to identify if an equation can be written as a self-adjoint equation, how we can write it as a self-adjoint equation, and when we can write it in the form of self-adjoint equation, we can find out these good properties. Here also let's see the proof, how we can prove it. Proof is very trivial, as we have proved the last part, where we have already said that it is the intermediate part for the next theorem. So if you have this terms equal to constant, since both f and g both are solutions, so I have already proved that this terms becomes constant. Now since at t0 f of, so see at t they have both common 0, so we are assuming t0 is the point where f and g both becomes 0. So if you just put t0 in this equation, so this equation should be satisfied for all the t between a and b. So if you put t0, the constant becomes k. constant becomes 0. So therefore the left hand side is basically Wronskian. F of t into g dash t minus f dash t into gt, this is basically Wronskian of two solutions up to functions fx and gx. So the Wronskian becomes 0. Since the Wronskian becomes 0, so they becomes linearly dependent. Next, see another important theorem. Let f and g be two non-trivial linearly dependent solution of this self-adjoint equation such that f of t0 becomes f of t0 equal to 0 for some t0. Then f and g then g of t0 becomes 0. So basically this theorem states that when you have two linearly dependent functions, linearly dependent solutions of a self-adjoint equation, if one solution have a 0, then the other solution will also have the same 0. So two dependent solution always have the same zeros. So in other words, if f becomes 0 at a point, then g also becomes 0 at that point. So let's see how we can prove it. So since they are linearly dependent, so their linear combination can be written can be equal to 0 where C1 and C2 are constants and at least one of them is non-zero. That is the definition of linearly dependent functions. Now since there are two linearly dependent functions only, so C1 and C2 both have to be non-zero. If C1 becomes 0, then C2 automatically becomes 0 or otherwise G becomes 0. Similarly, if we assume C2 is 0, then either C1 is 0 or f is 0. So for a linearly dependent functions where f and g both are non-trivial, that means f and g both are non-zero, then C1 and C2 both are non-zero. So this is the first observation we can make from here. Now we have already assumed that let f is 0 at a point t0. So if we just put the point in the equation, then what we get? We get C1 into 0 plus C2 into g of t0 equal to 0. But we have already showed that C1 and C2 both are non-zero. So which becomes that g of t0 equals to 0. So this ends the proof. So see, we are here just only discussing the steps of the proof. If we explain it, the proof maybe looks lengthy, but the logics are very simple. There's only 2 or 3 steps to prove this theorem. Okay, so it's when we write it and explain it, it may look lengthy, but actually there is only 2 or 3 steps to the proofs. So the proofs are very easy. We are easily can prove these theorems. Now next see another important and 2 or 3 more important theorems so that we can understand more about the properties of self-adjoint equations and why this theory is more important. So in the next slide, we see an important theorem which is Sturm separation theorem. What does it states? It states f and g be two linearly independent solutions. So till now we are talking about that how two solutions will become linearly dependent, and if the two solutions are linearly dependent of a self-adjoint equation, so what are the conclusion we can make? So here we are assuming that f and g are two linearly independent solutions, and then what we can conclude from there. So see, if f have two consecutive zeros, then there is exactly one zero between these two consecutive zero of f. So between any two zeros of f, there is exactly one zero of z. So there is no speciality about f and z. You are just giving them as a name. So the conversely also true. That means between any two consecutive zeros of z, there is exactly one zero of f. Let's see how we can prove this theorem in the next slide. So proof, let T1 and T2. So we are going to prove this theorem by contradiction. So we are assuming let T1 and T2 are two consecutive zeros of f, and if not, what happen? So if there is no 0 of z in between T1 and T2, if not means if there is no 0 between T1 and T2 of z, then what will happen? Then this ratio of f of t by g of t is already continuous, and g of t is not equal to 0 as per our assumptions, since and why it is defined is in between T1 comma T2. So in the interval T1 comma T2, if zt is non-zero, then this ratio is well defined, first of things. And then as per our definition of the, since they are solutions of the given self-adjoint equations, so they are continuous and they are differentiable. And also f is 0 at T1 and T2. So as per Rolle's theorem, so it satisfies all the conditions of Rolle's theorem, and as per Rolle's theorem it should be 0. The derivative of this ratio should be 0 at some point in between T1 comma T2. So this ratio becomes 0, the derivative of this ratio. Now what is this derivative actually? This derivative actually Wronskian of f comma g by g square. Now we have already assumed that gt is not equal to 0 in between T1 comma T2. So therefore it only conclude that the Wronskian should be 0, which means it should be linearly dependent, but as per our assumptions they are linearly independent. So that means our assumptions is wrong, that there is no 0 between T1 comma T2. So there is at least one 0 between T1 comma T2, so that gt becomes 0 in this interval T1 comma T2. So contradiction. Now if we want to prove there's exactly one, if you just suppose g1 has more than one 0 and then use the same above argument in by interchanging f and g, that means assume that f g of t by f of t is the ratio, is the given function, and then try to apply Rolle's theorem on it, and then you will get that there is some contradiction. So this is the proof of the Sturm's separation theorem. I am just going to explain one more theorem, just the statement, which is also very important, in the next slide. So it is Sturm's fundamental comparison theorem. So this is another important results related to self-adjoint equation and Sturm theory. And what is said that suppose there are two different equations. See, these two equations are two different, only q1 and q2 are different. So basically p are same, but the coefficient of x are different. Now if f is a solution of the first equation and g is the solution of the second equation, what we can make from this given results. Now we are also assuming that the coefficient q2 and is greater than q1 for all t. So if there are two consecutive zeros T1 and T2 of f, then there is at least one 0 g in between these two consecutive zeros. So when f and g are two solutions of the same equations, linearly independent, that we have seen Sturm's comparison theorem, and here f is a solution of one equation and g is solution of other equation. Here also we can make some conclusion that if q2 is greater than q1, then in between any two consecutive 0 of t of f, T1 and T2, which are consecutive zeros of f, there is at least one 0 of g in between T1 and T2. We are not going to prove it here, but this is also very important results. And here we are going to conclude this discussion, where we have seen the important properties of adjoint equation, self-adjoint equation, and their importance and the theories related to them, which are very important for the students who are going to do research in this area, or if you want to go for any competitive exams, these theorems and these results are very important and helpful. Thank you.